Folks, let's talk about the behavior of this LR circuit that has a couple of features. One is this switch S that can be either closed or not. Right now it's not closed. And then it's got this thing called a make before break switch, which you'll see here, which basically has two different ways it can be closed, but a connection can be made before another connection is broken. And so that make before break is oriented as you see, and what we're going to talk about is when switch S is first closed, how does this circuit behave? We do that by means of a loop rule statement. All right, and our loop rule, the closed loop when this switch is first closed is going to be that one. Okay, and when this happens, when we close this switch, well, there's an EMF induced in the inductor with a polarity like that because the inductor works against the change in current. When we close switch S, there is a current that changes from nothing to something, and the greater the rate of change of current, the more the inductor works against that change, as evidenced by we've seen that the induced EMF in an inductor is L di dt, which is to say that the greater the rate of change of current, the more the inductor works against that. So if we write a loop rule statement, we can start by saying V battery minus V inductor minus IR equals 0. There's a drop across each of these resistors, which of course we can write as just 2 IR. There's the same current in each of those. So this says that the battery voltage, which we should really just write as V, but that's okay, equals the EMF, which you'll see a lot of times is with an epsilon instead of a V, plus 2 IR. Okay, now we can say V, I'm going to turn VB into just V, that's a constant. And this VL is L di dt by definition, plus 2 IR. Now, this current changes, varies. And we also have an expression for the rate of change of current. So here we have an expression or a situation in which the rate of change of a function depends on the value of that function. All right, and that points us to a certain type of solution that you're likely used to. I'm going to write this as follows. I'm going to leave the 2 IR by itself minus V equals negative L di dt. All right, what I'd like to do is get the i's by themselves. All right, so that means I'm going to do negative L over 2R di dt is I minus V over 2R. Now, from a notation standpoint, we can make some use of the fact that we actually know what this is. What is V over 2R? Well, V over 2R is the current when this inductor isn't there. All right, and that inductor isn't there after a long time. It's there, but it behaves like it. The circuit behaves like the inductor is not there. And that's because what this circuit will do, if we look at I as a function of time, we close that switch and current tries to go from something to something much bigger right away. But the inductor works against that, thus decreasing the rate of change of current, but that decreases how much the inductor works against that. So the inductor doesn't work against it as hard, which means current can keep increasing, but at a slower rate. And then the current keeps increasing, but not as fast. And so the inductor keeps working, but not as hard against this. And the current basically does that until it reaches some long-term steady state amount of current. And look at this. Once this current reaches a steady state, there is no more rate of change of current, and the inductor doesn't do anything. So eventually it behaves the inductor behaves like it's not there at all. And so if this were a circuit without the inductor here at all, and we just had, well, this loop with 2R in it, this is the final steady state current. All right, so from a notation standpoint, it can be simpler. L over 2R di, dt equals I minus I final. It just kind of cleans up the notation a little bit. Okay, now we've got I that varies. We've got di over here on the left side. We've got to get all the I stuff on the same side. So what I'm going to do, if we multiply both sides by dt, I'm going to take all this stuff and shrink it up a little bit. Okay, so from here, I have negative L over 2R di is I minus I final dt. All right, and then I can take the inverse of both sides to move all the I stuff over here, all the R and L stuff over there, and I get 1 over I minus I final di is 2R over L dt. Don't forget that negative. Okay, now we integrate both sides. Current goes from nothing to some current at some time t. And that started at time 0, and we look at our current at that time t. So this integral evaluates to the natural log of I minus I final evaluated from 0 to I, and this is simply 2R over L times t. Now, evaluated from 0 to t, okay, yields the expression we have written, negative 2R over L times t. Okay, so this goes, let's see, natural log of, let's evaluate when I is I, okay, that's I minus I final, minus the natural log of 0 minus I final. This is exhaustive, which is to say that you might not write this in as much detail as I am, but that's okay. When we take the difference of two natural logs, that's the same as taking the natural log of their quotient. I minus I final over negative I final is negative 2R over L times t. Now, if we raise both, if we take e to the both sides, once again, I'm going to shrink this stuff up and group. No, not that part. Yes, no, mostly. This now gets us, this left side says I minus I final over negative I final is e to the negative 2R over L t. I haven't really helped myself because now I need to shrink again. But we get, let's see, I minus I final is negative I final e to the negative 2R over L times t. And then we move the other I final over there and factor it out, and we get I as a function of t. This is really I as a function of t is I final minus I final e to the, so that's I final times 1 minus e to the negative 2R over L times t. Okay? Now in this case, this quantity has to do with the time constant, all right, of this exponential growth, all right, and if we say that this is, that's a factor that says, well, if I continued at its original rate of change, it would get all the way to I max in one time constant tau. All right. And in this case, that time, because we can write this generally as I as a function of t is I final 1 minus e to the negative t over tau. So this says that our time constant here over tau is L over 2R. Generically, we say the time constant is L over R, but our effective resistance when our switch is in the orientation, or when this switch S is closed and this make before break is in the orientation that it showed, our effective resistance is 2R. Okay? Okay, now we can talk about, well, what happens when we move that make before break? All right, well, when we do that, current that was rocking around like this in a steady state suddenly is shut off. All right, and so what that does is we go from current this way to no current this way, and this thing says, oh, the inductor by its nature says there's a decrease in current. I'd like to keep current going. All right, so when we move this make before break, this circuit behaves like, well, it really does just have, it really does just have inductor R. That's it. That's all that the circuit has in it. All right, and like we said, when we shut off the supply of energy from that power source, this inductor works against that change in current and tries to keep producing current in that direction. All right, so our loop rule statement now, we can say, I'll write it as the EMF produced by the inductor minus IR is 0, or the EMF produced by the inductor is equal to IR. Well, I changes because this is L di dt. And what we can justify here, I think, is that, well, why is there current? All right, there's current because the inductor has an induced EMF. The inductor has an induced EMF because the current is trying to change from something to nothing. Right? When this make before break is moved, we go from a steady state current I is V over 2R to, well, eventually nothing. So there's a decrease. The rate of change of current is negative. So that allows us to put a negative in there, which we'll need because if we rewrite this to get I by itself, I is L over R. I'm going to do this, and I'm going to move the dt over there. And there's a negative. There's an equals. Let's do that. All right, so now I can say 1 over I di is negative R over L dt. And then we can integrate both sides. Now, I goes from some initial current, right? And this initial current is the steady state current from our previous slide where this switch S was closed. And later there will be some current that we can express as a function of time. And we'll say, let's start our clock over from time 0 to some later time t. All right, this won't require so much space. Hopefully I can get it all in here. So this just says, well, natural log of I evaluated from I naught to I is equal to negative R over L times T, evaluated from 0 to T, but okay, that just yields the expression we see there on the right. Okay, so this is ln, well, when I is I, okay, minus when I is I naught, that's going to be minus the natural log of I naught. But if we're subtracting two of these natural logs, we can write this simply as the natural log of their quotient. Negative r over L times t. And then if we raise both sides to the, is that how you say that? We raise, well, we do this. E to the both sides, fine. So e to the natural log of I over I naught is I over I naught. And this is, okay, yep, e to the negative r over L times t. Or I as a function of t is I naught e to the negative r over L times t. Or in general, I naught e to the negative t over tau, where in this case our time constant is L over 1r, one factor of r, as in our, in our effective circuit now, there's a single resistance. Okay, and so what does this current do? Well, it looks, excuse me, let me do the following. This current as a function of time does this, where here is our I naught, which is the same as the I final from before, right? V over 2R, right? And there is some initial rate of change of current where if the current continued at that, or if the rate of change of current continued at that rate indefinitely, then after one time constant t, tau, the current would be nothing. But it doesn't change at that initial rate of change because, well, the more the current is initially changing, the more the inductor works against that change, which makes the current not change quite so fast, which makes the inductor not do so much, which makes the current still decrease but not as fast, which makes the inductor not do so much, which makes the, and that's the nature of this exponential decay. Okay? So there's a couple of RL examples. Adios.